Okay. Okay. So initially I wanted to talk about K theory, but it all got shifted, and I will now be talking mostly about index theory, and K theory will be just defined briefly just so that I can use it for something. And this is also a series of talks because I cannot fit everything in one. There are many things which have to be defined. Obviously, I will not prove anything, but even to define it, it will take at least 2 talks. So this will be part 1 of that. So what I'll be doing is index theory. 1 second. Is it visible? Okay.
Yes.
Okay, so okay, before I get to index theory, there are a lot of things I have to first build up. So first, let's start about talking, defining vector bundles. So what are vector bundles? So let's first start with a manifold M of dimension n, smooth. I'll always be doing smooth functions, smooth maps and everything here. Smooth, compact, and without boundary. For index theory, you can relax this to a certain extent, and this to a certain extent, and this to a certain extent, but this is the easiest or easiest in some sense case. So let's do this. Okay, so what is a vector bundle? So vector bundle will be, so a vector bundle over M. So there is always a base space, and I'll be talking about vector bundles over that. And this will be a family of so if P is a point in M, to each point in M, I will associate a vector space EP over M, a vector space of, let's say, dimension K or rank K. I will always keep K fixed, otherwise it won't be smooth. So yeah, just pictorially, if you think of it, it is just, let's say if we had a circle, I'm just associating some vector spaces there. So each of them, there's one. And because of this, I can define, let's say, this. Belong to M. So just take the disjoint union of all these vector spaces, and this will be called the total space. And from this total space, there is always a projection, E going to the manifold, which just takes any vector. This vector will belong to some vector space EP, and I'll just take it to P. So pictorially, what I'm saying is, if you are in some vector here, I will just project it down to the point here. So if you're in a vector here, you will be projecting to this point, right? So that's your projection map. So this is what I'll call projection. And M will be called the base. Okay, so 3 things. Again, there was no reason for me to say M was a manifold here. This could have been any topological or any space, and I can do all this. The reason I want to have it as a manifold is I want to define smooth compatibility of these vector spaces. So what I want now is I want P's to be glued smoothly. So what do I mean by that? So what I mean is, so for every point, so let's call this the definition. For all P in M, there exists a neighborhood U of P and a map Phi. So I'll index it by the same open set, which will be, so take pi inverse of U. Pi was already defined, it was the projection map. I will take the inverse image of that. And I want this to map to R to the K, U cross R to the K, where K is the rank, and I want more properties for this. So such that if this, when it is restricted to one of the fibers, so if I restrict these to fibers, so these are again bunch of collection of fibers here, right? When you take inverse image over your projection mapping, any point will give all of its fiber. Inverse image of that is all of its fiber. So this is a bunch of fibers, and when I restrict to fibers, not the P, I can take any Q here. I want this to be an isomorphism. Is a linear isomorphism. For all Q in our open set. So this gives us a diagram like this. So this was the map I defined, which was phi U. I also had a projection mapping to M, or rather to U. This is just the restriction of the projection map. And here I can always define projection just to the first coordinate, right? It's U cross something. What I also want is, I want this to be a commutative diagram. Right, so I want two things. One is this, and another one is this. This is kind of giving compatibility, saying, so if you take P cross RK here, that will be isomorphic to EP. Basically, that's what I want, right? Because, yeah, I'm just trying to model these fibers according to this. Okay, then I also need a smooth compatibility condition. That is, if I have two open sets intersecting, then we want that this phi U. So I'll get two maps, and I want this going from the intersection. This to be smooth. Okay, so these are the things I need for to have a smooth vector bundle. So every point on your base, so you can draw a picture here. Let's say I have this base space here, and on the top I will have, let's say, rank 1 bundle, which is just like this. So then if I take this point here, what I want is, I need an open set around it, such that when I take an inverse image of that open set, which will give me all these fibers, that I kind of want it to be isomorphic to, I just want it to be isomorphic to this interval cross R, that's all. Right, so that the projection like this and like this, they are all compatible. Basically, that's what is happening. And in some sense, I want the transition functions. So these phis will be called coordinates or trivializations, whatever. When I do transition from one trivialization to another, I want it to be going smoothly. Okay. If I said it was just continuous, then this would be continuous class category of vector bundles. Cool. Any questions till now? Okay. A slightly alternate. Did someone say anything? विश्वदीप सुनाई नहीं दे रहा है तू जो बोल रहा है.
Go ahead, write in chat also.
Okay. तुम लोग को सुनाई दे रहा है क्या? मतलब मेरा नहीं, विश्वदीप
ब्रेक
का.
ब्रेक हो रहा है उसका वॉइस, मतलब लेकिन
Okay.
उसने बोला है शायद गो अहेड बोल के बोला है.
हाँ वही ठीक है. Okay. Okay, so this was one definition. I will just give a small alternate definition which may or may not be useful to think about. So I had a manifold M. So let me take an open cover of M. So alpha belongs to some index set. Be an open cover of M. Let's take phi alpha beta. So let phi alpha beta be maps going from intersection between alpha beta to GL and GLK. K of R smooth. So for each alpha beta, I will, so U was an open cover, and for each of them, I want to have such a map, which has more properties, such that for, so if you take a triple alpha, beta, and gamma, then you want phi alpha beta compose phi beta gamma to be equal to phi alpha gamma. So basically, you want the composition to like hold true. Okay, so then, so if you have this information, this data, this also defines a vector bundle. So this phi alpha beta defines a so this is an easier way to give vector bundles, because if you have a circle, what you can do is you can take open covers which are like this, and you can take this, and you can just give a map from this open set into GL K of R, and similarly give a smooth map into GLK R, and that automatically will give you a vector bundle, because you don't need to check actually, what am I saying? You just need to give things on the intersection here. Sorry. Only on the intersection you want to give a map into GLK. So that's a single map. Or you can say, because it's disconnected, there are two maps. So just giving this information will define a vector bundle over this. So what you're doing is on these two arcs, you will say on the arc, you will just say it's a trivial bundle. So it's some trivial RK cross this. On the bottom arc, you will have this cross RK, and where they intersect, so there'll be an intersection point here and intersection point here. So where these two vector bundles are supposed to intersect, you will have some matrix multiplication of the these things. So you will twist those vector bundles and you will attach them. So that's how you get one vector bundles. So trivial examples will be, so instead of taking RK, if I took just R, it will look like like this, cross like just lines like this. And on the bottom, if it's like that. And if I just attach these two directly like this and this, what I'll end up with is I'll just end up with the trivial cylinder which I was drawing before. So it's just like a infinite cylinder. Right? This is one. So this is S1 cross R. Wait, G. If I did not do that, if I just pasted this as it is, but if I instead took this and twisted, so let's say took this and I stuck it on the other direction, just like a twist. If I do one twist over there, it will look like, okay, the picture will look bad now, but so if I do that, it will, yeah. So if I instead, if I twist it over here and glue them, then it will look like this. This is called the Mobius strip. I've drawn it finitely, but this all goes infinite here. So these are actually vector spaces. So over each point again, you still have a circle in the middle here. So there's always one circle in the middle and you have vector spaces over it. But these two, this is one vector bundle. This is the trivial one. This is a Mobius strip. This has a twisting in it. So these two are not the same, but they are still vector bundles. Okay, so there are ways to show it as topologically different. So that leads us to what does it mean to be isomorphic? So, okay, are there any questions still here?
So basically, whenever you are saying, suppose you start with a smooth manifold M, and suppose then you have a vector bundle over that manifold, then does it have a manifold structure always, like?
The vector bundle, yeah. So the total space of this vector bundle. So if this is E, so this will be the total space.
Yeah.
This will also have a manifold structure automatically. Because so your coordinates will be, because I had defined this trivialization here.
Oh yeah. So
these are automatic. These will automatically become
these
coordinates.
are local stuff, like, right?
Yeah, exactly. If I chose my open set to be a coordinate also, so this will just be Rn cross Rk. That's right. It'll automatically have a smooth manifold structure.
So, what will be the topology on this E?
Topology on which one?
Well, E.
On E.
Yeah.
It will just be topology induced by. So you want to topologize these, right? I want to say these are open sets. So I'll take the topology here and induce it here.
Okay. So, and these things will ensure that it's different, the compatibility with this.
Yeah. So smooth transition will ensure, like, obviously homeomorphisms also, like. Yeah. Yeah, basically what I wanted to say is this, what it will do is if you take an open set on the bottom, you take an open set here and you take the inverse image of that. So take all the fibers going through those points. That will be an open set on the top here. So this will be an open set on the top. And you will be able to trivialize it. So what one thing to take away is vector bundles basically look like some Rn, or like some open set of Rn cross Rk. But when they glue, when you're like sticking them together, that is where some twisting happens or something non-trivial happens. So it's not all vector bundles will not look like this. They might have some twisting. Okay, so that is the important thing we are going to try to capture later. Okay, so first, what do I mean by isomorphisms? So let's say two vector bundles, let's say E and F, over the same manifold M are isomorphic. If there exists a map which goes from E to F, smooth, such that so I will have this commutative diagram again. Both will have projections. I want this to commute. So basically what I'm saying is fiber over some point P here will go to fiber over the same point P here. Okay, that's all I'm saying. And what I want is then when E is restricted to that fiber from EP to EP, FP is a linear isomorphism. Okay, so that's all I'm saying. So over two things are same if over each fiber or over each point, the vector spaces you have, those have to be mapped isomorphically to each other. And the whole map from E to F should be a smooth map. So it's smooth and isomorphic on each fiber. Okay. Yeah, sorry, skip a bunch of things. Oh, there's something in chat. Your second definition says fiber bundle its structure group will be vector bundles. Fiber bundles with structure group, this will be, yeah, it will be vector bundles, yeah. But fiber bundle is a more general definition than this. So I'm not going there. Okay. What I can do is operations. So there are operations on bundles. So if you have any vector space, so let's say we had vector spaces V and W, or then we can talk about what is V direct sum W, V tensor W. You can take the dual of V. You could also do, I don't know, you can do like a wedge product of V, whatever. So there are a lot of operations you can do on vector spaces to get new vector spaces. So here you're starting with vector spaces, ending up with vector spaces. You can do basically all of these on vector bundles. So if you have two vector bundles, E and F, you can add them fiber wise. So at each fiber you add them and you get a new one. So if you have, like, let's say example E comma F were vector space vector bundles, then E direct sum F will be, so take each fiber, just add them, right? And what will happen is if your direct sum here is good enough or nice enough, then this will also patch up smoothly. A technical way of saying it is if the operation on the operation on these vector spaces is a smooth functor, then it goes for infinity. Okay, so if you have basically nice enough operations on vector spaces, it will give you nice enough vector bundles. And for the most part, the things we work with will be these, and these are smooth functors, so you don't have to worry too much about that. Okay, that is vector bundles. Now I just want to say what is a section of a vector bundle. Section of a so again I'll draw the usual vector bundle I had. This is a projection map. So a section will just be a map going in the opposite direction. And what it will do is, if you have any point P here, P, it will give me some vector over that point. So it will give me some vector here. Or it will, okay, so for each point, it will give me a vector in that point's fiber. So that's what I want to say is a section. So definition wise, so C infinity map, which goes from the base to the vector bundle, such that if I compose it with the projection, so if I, it's the other way, I think. Which way is it? It's like go up and come down. Okay. From M to M. So if I compose the section with the projection, I need to have the identity map. So this is the identity map. So that this basically means for each point, I'm giving some vector in the bar in the fiber. Okay, and I want this to be smooth. So if I take another point here, I'll get another fiber, and I want this to move like smoothly here. Okay, so this for a section will basically like draw out like a line here, like some squiggly line like this, and that's a section. Okay, so just small definitions here again. Definition, I will denote gamma of E to be the all the sections. C infinity of E. Okay. So if we had a trivial bundle, this trivial bundle, so any manifold cross Rk will be called a trivial bundle. So if I have a trivial bundle like this, and the usual projection to M, then the sections of this will be, what will it do? It will, so for every point here, so every point P over here, I will be getting a point and some function of P, because it's a real number, which is smoothly varying. So any section will look like P going to some P, because it has to be over the same fiber, and some function or some vector in the real numbers. Any vector in the real numbers is just a real number. So I will just be associated this. And because I said this has to be smooth, this function will be a smooth function now. So all sections over our trivial bundle will just be C infinity functions over M. So if I took R over here, these are just C infinity functions. So in a way, I want to say sections are just more generalization of C infinity functions. So instead of just working with C infinity functions, at some point, I'll just start working with sections because they capture functions and more. So here I had no twisting. I could have introduced twisting of this, and that will capture something more. So that is there. Any questions till now?
So I have one more question. Like, is the image of a section, is it a manifold again? Like, which or smoothly isomorphic to the original manifold?
Yeah, it has to be isomorphic to this manifold.
Right.
Because it will be a one-to-one map. this way. I think, yeah. It should be a one-to-one in what is it called? It's
1-1. Yeah.
1-1, and there's something if the derivative will also be 1-1. I forgot the name.
Immersion.
Immersion, it's a 1-1 immersion. Probably it's also proper mapping, so it will be an embedding. So yeah, this will just embed M into your bundle in a squiggly way. Yeah. Okay. Connections. So now I also want to talk about what a connection is. Yeah, these are basically a lot of definitions. Again, chat. Maybe also try showing that zero section is a continuous map. Yeah, so you will always have a zero section here because these are vector spaces here. At each point, it's a vector space, and vector space have a canonical zero for them. So you can take any point here and map it to the zero thing here. That is called a zero section. So any point going to the zero of this vector space here, that will be very like trivially isomorphic to your M without any squiggly thing. But yeah, zero sections may or may not be important. I don't know if I need them. Okay. So what is a connection? So so if you have a manifold, let's say sphere this time, and you're given vector fields on it. So vector fields are just like arrows on your manifold. What you can do is you can take any C infinity function on the sphere and you can differentiate it according to the vector field. Basically, that means do directional derivatives. Okay, so given any vector field, given any vector field, X. So X is a vector field. Let's just say that. And F is a C infinity function. Then we can differentiate. We can write XF, which is the directional derivative of F. Right, so at each point, X gives me a direction and F is just a smooth function. I will differentiate it in that direction, and that will give me a directional derivative. Okay, and this is something I want to capture in sections now. So we had a vector bundle. I want to somehow, I have sections now. I want to differentiate those sections. Right, so F was a section also, and I have a nice way of differentiating it. I will try to define what it means to do it on sections. So definition. Nabla on E is a map. So Nabla will be I will define X of M to be vector fields. So these are all C infinity vector fields. Just to take it as definition, C infinity on M.
So vector field we can think of as section or tangent vector.
Yeah, exactly.
same?
So it is exactly that. So this is actually the section of tangent bundle. So this is, if I didn't define the tangent bundle, but if you take tangent spaces at each point and it will glow up because of certain things, that will give you a bundle. That will be a tangent bundle. And if you take sections of that, that will exactly be your vector fields. Okay. But if you don't like that, just treat vector fields as they are. So I want to have some kind of an action of vector fields on my sections. right? And it has to give me a new section. So take a vector field and differentiate a section and get a new section. That is what I want to do. So that will be written as nabla xs. Okay, that's just notation. Okay, maybe I'll write it better. So x and s will be taken to nabla xs. So you're differentiating s with respect to this vector field. And this will have a lot of properties. First is nabla xs is R linear on this. So basically, if I have S1 plus S2 here, so if I had like nabla x of A1 S1 plus A2 S2, where A1, A2 are real numbers, then I want this to happen. Okay, so A comma A1 comma A2 real numbers. So that is what it means to be R linear. I also want it to be linear in the other term. So is C infinity M linear in the vector fields. So if I have f1 x1 plus f2 x2, where f1 and f2 are C infinity functions, it makes sense to talk about this. This I want it to be equal to f1 nabla x1s plus f2 nabla x2s. Okay, so this here it was just linear with R put only constant terms, but here it is also linear with functions as coefficients. So now what would happen if I put in functions over here instead of instead of constant? Suppose I had a function here. There is a rule for that, which is if you have a function here, it will be differentiated in a different way. So you will want it to have a sort of product rule. So since it was just a function, I want to differentiate it with the vector field. Then take the function out and differentiate the section. So it's basically x is applied to this first, then x is applied to this first, this later. So this is a product rule, or it's called Leibniz rule. Okay. Yeah. Okay, so these are connections. So this is a way of differentiating sections according to vector fields. So these are directional derivatives of sections. Now that I have this, I didn't say this, but I didn't prove this, but you can say there exist connections on every vector bundle E. So it is an easy task to prove using partition of unity that connections always exist. So you don't have to worry too much about that. Okay, so once we have a connection, we can talk about so as I said, these vector bundles, when I had defined them, where did it go? Yeah. So there was some twisting happening, and when you glue it, right? Some of them don't have any twisting, some of them do. So this twisting kind of introduces, let me say, curvature in some sense, and we want to capture that. So we want to capture how these things are twisted, so that you can talk about curvature of a so how do I define what a curvature is? So let's take any two vector fields and any section. Then the Riemannian curvature tensor. So this will be a function of three things. One, like two of them will be vector fields, one of them will be just sections. This will be defined to be. So what you do is first directionally differentiate S with respect to Y, then differentiate it in another direction and take their difference, right? So differentiate with respect to Y, then X, X, then Y, take their difference. And also a further thing you will have to subtract is XY. So this is also a new vector field. I'll say what this is. So basically what this is measuring is how far is, so this is like a commutator and this is also a commutator. So if this is not zero, you're kind of saying how far is it from being zero. So you differentiated flowing in one direction and differentiated flowing in the other. And you did other direction, then like this. Maybe I'll draw a picture. So what you did was first, let's say you flow like this, you differentiate in that direction. Then you go like this and differentiate in that direction. Or you go like this first, differentiate there, then come back like this, differentiate. This is all happening infinitesimally small place. So think of this as happening very close. So these two derivatives, how are they different? How different are they is what curvature is sort of measuring. Okay. So here I have to say here, this xy, this is a commutator of vector fields. This is nothing but xy minus yx. Okay, so this applied on a function will just be like this. So xf is another function and you can differentiate that function again with respect to a new vector field. So this makes sense. And you're basically saying how far is this commutator versus this commutator. That is what curvature is measuring. Yeah, I don't really have a good picture of this. So even I don't know how to intuitively think about it. So this is all I can say. So R is called the whatever, it's called Riemannian curvature tensor, not very important. Properties of this is R is C infinity of M multilinear, which means if you take any, put F anywhere, it will just come out as F like this. Okay, you can also put it over here. And basically by some properties of how I've defined it, things will cancel out and this will again be F times X, Y, and S. Okay, so that's what it means to be C infinity multilinear. Obviously it's a linear, as in if you add two things, it will split up as you want it. Okay, so that is there. And also, so what this allows is, this will allow me to talk about things at a point. So vector field, when I evaluate it at a point, it's just a vector tangent. It's just a tangent vector, and sections are also just a vectors at a point. So because of this C infinity linear property, I will not get to why. I can talk about what it is at a single point. Because otherwise you would have to differentiate and you will have to move to another point and compare it to those points, right? Yeah. So ideally, like by definition, you need to know the values in a neighborhood, but because it's C infinity M linear, you don't need it values at neighborhood, you just need it at the point. That doesn't make sense, it's okay, just forget it. Just it makes sense to talk about this thing at a point. And what this has is, this is skew symmetric, is skews in XP and YP. So basically, if you flip xp and yp here, you'll get a negative sign. Why do I care about that? So what happened to, if I rebrand whatever I was writing, it's just saying that R takes two tangent vectors and it maps sections to another section, right? So it will go take a section and it will map section to another section. So if I give two vectors, what it is giving me, it is giving me a linear map between the sections. Or I can write it as, it's giving me a homomorphism like this, right? So if I give you two tangent vectors, I'm getting a homomorphism of my vector spaces. If I was able to make this isomorphic to Rk, so if I just pick a basis here, this is actually a matrix because it's from the same thing to the same thing. It's just a square matrix. So what I'm getting is at each point, this Riemannian curvature tensor is nothing but a matrix. Yeah, it's just giving you a matrix, right? Again. And since this was skew symmetric, taking two vectors and interchanging them, it will give a negative sign. So in some sense, it's also behaving like forms, because forms, when you interchange two things, forms also take in two vectors, which you interchange, it will give a negative sign. So basically what R is doing is, R is actually a matrix. So you'll have matrix valued things, and each of them, when you flip x and y, will give you a negative sign. So each of these things, entries, will be a two form. So R is actually a matrix of just of two forms. So it's like a square matrix here where it's like omega 1, omega 2, whatever, and each of these are just real valued two form. Okay, and again, this could only be done if I chose a basis for this, right? If without a basis, I cannot say what the matrix is. So what is the basis? Basis will come from the trivialization I had done before. So in a neighborhood, I can pick a consistent basis. So R is a two form, matrix of two forms only in a neighborhood. So note, R is a matrix of two forms in a neighborhood of P. And if I change this neighborhood, I will get a different basis, and that will give me a different matrix of two forms. Okay. Are there any questions till now? I will tell you why I care about this, or why you would care about this in a bit.
So this xy square bracket you are defining, so is that also vector field?
That's also what?
Is that a vector field? The square bracket xy?
Yeah, it's also, this is also a vector field. So this so vector fields I can characterize by saying it differentiates functions. Okay, in some particular way.
It's called Lie bracket.
Yeah, so this is called the Lie bracket. So it
And
say.
yeah, so when you say there are exist connections, so we can just define everything to go to zero, right? So that also.
Everything going to zero will not give you the Leibniz rule, I think.
Okay.
Because if you just say all of these are just zero, if you
That
take
first term is
okay. Yeah, this term will not be zero. I mean, if you take this to be non-zero, this and non-zero, it shouldn't work. Yeah. So the zero is not a connection. This is actually an affine space kind of.
Oh.
So like it's if you think of set of all connections, it is basically a vector space, but it is like moved away from zero. So there is no 0 there. So if you move it, if you bring it back to 0, then it becomes like vector space, but it's otherwise it's an affine space. So you take affine linear combinations of these and you'll still get connections. Okay, but yeah, so I didn't really want to go to that. It's a simple definition how you get it, but it's a distraction from what I was saying. Yeah, any other questions about the Okay, so what I have defined till now is I defined a curvature thing on my vector bundle somehow. And locally, if I restrict to open sets, I get a matrix of 2 forms. My goal is to get a global invariant which captures how I have twisted things. That is my goal. But these, because they are only defined in open sets, these will be local invariants. So I need a way to patch these up, right? So I have on one open set, I have a matrix, another open set, I have a different matrix. Now I want to see how they change when they change, when you change coordinates, right? Or when you change the basis. So how do these change of basis, right? So I'll not say what it is. It's a theorem. The theorem is the best case scenario for us is if I change the basis, this matrix of 2 form did not change. That is the best case scenario for us. Then we can say, oh, I will locally define this matrix for this open set, another matrix for another open set. And because on the intersection, they are same, I can define something global. But that is not the case, unfortunately. So if I have a change of basis thing, which I had defined before, alpha beta going from u alpha intersection u beta gl of k. So this was in my alternate definition of a vector bundle. So this is what is called a change of trivialization or transition map or whatever. It basically takes you from one open set to another. I'll just call it change of basis. Then the matrix of 2 forms I had for the open set beta, it will be equal to alpha, but you will have to multiply it by phi alpha beta inverse and phi alpha beta. So phi alpha beta at each point is a matrix. I'm just taking the inverse of that matrix. And this is also pointwise a matrix. So this multiplication makes sense. And when you change bases, it just changes like this. Okay, so yeah, so what we wanted was it is actually same on the change of basis, but it is not. So what we can do is we can find some function of these which are not, which do not change. So for example, let me call determinant of R to be determinant of omega alpha for alpha. So locally I can define these, right? So this makes sense. But since determinant, when you apply A and A inverse to it, it will cancel off. When I did a change of basis, this would have been equal to determinant of P alpha beta inverse omega beta P alpha beta. But since properties of determinant, these two will cancel off. This will just be determinant of omega beta. So determinant is actually well defined. So determinant of your matrix of 2 forms is actually well defined now. Right, so that will give you a global 2 form. So this is it's actually global 2k form, because when you take determinant of two forms, this is a k by k matrix, there'll be k multiplication. By multiplication of two forms, I just mean take the wedge product of those. So yeah, so you'll get a 2k form. So this is a globally defined, well-defined 2k form. In general, if I have polynomials p of matrices, so if I have polynomials of x, let me write just polynomials of xij such that p of a x a inverse is equal to p of x. Okay, if you have such polynomials, then you can easily define p of r to be those polynomials locally, and because change of basis is like this, it will give you a well-defined thing globally. So these are called invariant polynomials. So invariant polynomials p. So any invariant polynomial p will give me a global 2 form, global 2r form, for some r. Okay, so this depends on nabla. Okay, so this is a global 2 form, 2k form. Another theorem I will just mention here is, without proving, this 2r form p of r is closed. That is d when I apply it to pr equal to 0. What that means is this will give me a cohomology class. So that will define a cohomology class in p of r in the cohomology. So this is the Dirham cohomology. Okay, never mind, forget that. Just in the cohomology of M, this will give me a class because it's closed. And the theorem is this class is independent of nabla. Okay, so initially I had chosen a nabla to define my curvature, and I used that curvature to define this form, and I saw that that form is closed, so it is giving me a cohomology class. But what it turns out is this class is independent of the chosen nabla. So this boils down to being a topological invariant of your vector bundle. So what happens is this will be this is a topological, whatever it means, topological invariant of the vector bundle, not of the manifold. It is of the vector bundle. Okay, so now what I have given you is this P will give you vector bundles. To take any vector bundles, this will associate to you a element in the cohomology. So these polynomials give you a way of associating cohomology in a topological way. Any questions till now?
So it is called Chan-Weil map, right?
Yeah. So yeah. So what is this? These are called characteristic classes. So these maps P. This is called a characteristic class. Characteristic class. And this way of defining using forms and local things, this is called Chern-Wave theory. But whatever, these are the important things. It's a topological invariant of your vector bundle. And what it is measuring is, it is measuring how you have twisted your vector bundles. It forgets everything about the connection you had put. It's just capturing how you are twisting your vector bundles. If
I think Vasu, it will be better if you write coefficient of the cohomology ring, because you are dropping dr from there. I mean, if you write,
yeah, it just makes it confusing. This is just
yeah.
dr r, but it just makes confusing, so I don't want to write it. It belongs to a de Rham cohomology, but yeah, because it's all isomorphic, it's the same. Yeah, and yeah, any other questions to you? Okay. Maybe just one example will be if you took trivial bundles RK. The characteristic class of any of these of this M cross RK will always be 0 because it's a trivial bundle. It's basically saying no twisting. So it is kind of capturing what we want. Okay. Why this is, again, it will take me a while to say that. Yeah, actually it's time. So I'll just stop here. So the K theory and something, I'll do it a little bit more later. So this will probably not be part 2. It will be 3 parts. If people are interested, you can come. Yeah, I'll stop here now.